Hi, and welcome to the second half of the Power and Ground lecture for A212. So up until this point, we've thought about connections on a schematic. So if we have two different points on a schematic, both connected to ground, we've thought of those as being the same voltage. So we think of them as being the same point on the schematic, the same net, the same voltage, all those meaning the same thing. So no matter what side of the schematic they're on, complete page, separate page even of a schematic, we can name them the same thing and they are the same point and they have the same voltage. That's what we've thought of so far. If we do that in the real world, though, we have to use a wire to connect those 2 points. A wire is a conductor, but there aren't any perfect conductors. So that means that there's going to be some amount of resistance to that wire. In most cases, it's really small, but we have to understand that it's there, and there are some situations where it's going to make a difference. So there's some resistance to that wire. If we think about a power wire, we have hot, neutral, and earth. So there we have 3 connections, 3 wires running next to each other. So each of those wires, or at least hot and neutral, are going to have that conductor surrounded by an insulator. So if they're running next to each other, then we have a conductor, an insulator, and a conductor, which means we have a capacitor. So it's capacitance between those wires. Also, because of the magnetic field created by current through these wires, the wires also form inductors. And none of these things are huge, and none of these things are going to be something we have to worry about in every situation. But we need to understand that they're there, and we're going to talk about how they do make a difference for us on a regular basis in audio. So if there's any current running through a wire, because we now think about the fact that it has some resistance to it, that means there's going to be a voltage drop across that wire. Again, we're talking about small differences, but they can exist. So let's think about hot and neutral. They have the current flow that's powering our circuit, whatever the load is we plugged in. So we just think of a lamp as the easiest example. So there's current flowing through those wires. Because they have some resistance, they're going to drop some of that voltage. So if we have a complete 120 volts AC, RMS AC at the wall outlet, we might not have every single bit of that for the lamp. We've talked already about how the voltage supplied by the power company can vary a fair amount, so we need to have some flexibility inside our circuit to deal with that. And this is another part of that, so we're not going to get every bit, but we're not talking huge amounts, maybe a volt at the most. It's just not significant. If we have a big enough wire that it's going to be able to pass the current we need without overheating and causing a fire, then the resistance is not going to be that much of an issue. So we don't really have to worry about it for hot and neutral. So we can look a little bit at that. So a 12 gauge wire is what is typically used for 20 amp circuits, which is the typical kind of circuit you would see in a house. So if we were to use, and that has 1.59 ohms per 1,000 feet. So if we ran a 60 watt light bulb 500 feet from the outlet, how much voltage would the light bulb drop? So we know that's going to be a half an amp, 60 watts, 120 volts, half an amp through 1.59 ohms. So we're going to lose 0.8 volts if we run at 1,000 feet. Now that would be 500 feet away. So if the light bulb was 500 feet away, we have 500 feet to get hot over to the light bulb, and then 500 feet to get neutral back. So we lose a bit less than a volt. Again, not an issue. And 500 feet is a long way to run a power cable. So again, this is not something we're going to worry about with hot and neutral. So let's keep going. Think about earth. And maybe I'm talking about what's going on in these wires for no reason. Maybe I'm not. We'll get there. So what about on earth? Should there be current flowing on earth? How much? We know hot and neutral have whatever current the device is using. So what about earth? So theoretically, right, we've talked about the only time there should be current flowing on earth is when it's protecting you from being electrocuted or someone else. Something bad has happened. Earth is protecting people. So theoretically, there's no current flowing except in those cases. In those cases, I don't think we're going to be concerned about noise or anything that that these issues might cause. Right, because we're just trying to protect someone. However, let's think about what's going on. So we know that the earth wire is running next to hot and neutral. There's current flowing through hot and neutral. So what happens when current passes through a wire? Well, we know it drops some voltage, some things like that, but it also creates a magnetic field. we know that a magnetic field induces current on another wire. So we have current flowing through a wire, which creates a magnetic field. That magnetic field then can induce a current in another wire. That's how transformers work. So we've seen that work already. In this case, though, we have hot and neutral. There's current flowing through them. Earth is sitting next to them. So they're going to induce some current flow on the earth wire. That's just going to happen. Now, fortunately, the hot and neutral wire, because current flow has to go up through hot through our device and then back through neutral, that means they have opposite but ideally equal current flows on them. That means their magnetic fields are going to be opposite but equal as well. So most of that magnetic field and the current it will induce is going to be canceled out because hot and neutral are right next to each other. So there's some wires where the three conductors are held in place so that they never change how they're laying, and they always lay with earth in the middle and hot and neutral on the two sides. Cords like the one in the picture here aren't going to do that. They could have some variation in them, but still they're going to be held pretty close to each other. But if you're using conduits, which we've already talked about a little bit, then there are three individual wires running in there, and how close they are to each other is going to vary just how it's running in the conduit. So in that case, we can have times when hot is much closer to earth than neutral is. So again, this is going to cause some amount of current to be induced in earth. This is not something we're going to try and fix. We can't change that. That's just a fact of how electricity works. But it's something we need to understand is there, and we're going to see what problems that might cause. So here I was a little bit early on my slide, but so here's what's going on, right? We've got these two currents flowing. It's going to create a magnetic field. That's going to induce a current. So that means that we're going to have a current flow on Earth that represents something like what's flowing through hot and neutral. So in our case, a 60 hertz sine wave. We're certainly not going to have the same amount of current that's flowing on hot and neutral, but some amount, lesser amount, is going to be induced on the earth wire. Another thing that we're going to have is noise that's induced from other electrical devices. So fluorescent lights, for instance, they only use a portion of the waveform that's given off by the power outlet. That means that they're going to create some distortion as they turn on and off and grab portions of the power. So instead of a real nice, pretty sine wave, we're going to see a sine wave with little things added to it. Little spikes and extra bits to the waveform. Those are all going to be higher in frequency than the 60 hertz signal that we've started with. So we can simply high pass and get rid of them. That high pass will be a capacitor connected from hot to earth, and another one connected from neutral to earth. That'll get rid of all that noise, that extra signal that we don't want, and get back to just a nice sine wave. However, that means that extra signal, that noise, is going to be filtered down through earth, so we also have that current on earth. So we have the noise induced, or the sine wave sort of induced from hot and neutral in their magnetic fields. Then we also have all this extra distortion and noise that electrical devices add to the sine wave that we want to get rid of. That's also going to go through our earth connection. So there we have two different kinds of current that are flowing through earth now. The chassis piece of equipment has to be connected to earth for safety. That way, if you touch it, something goes wrong, you're not electrocuted. That's good for us as audio people because it also means that any stray radio or electrical signals in the air trying to get to our audio and mess it up first come in contact with the chassis, which is connected to earth. And because of that chassis acts like a shield and gets rid of the noise, doesn't allow it to get to our audio. But that means it sends it to earth. So now we have this extra noise or whatever we're filtering out of keeping it from getting to our audio. That's also a current on the earth wire. There are going to be power transformers inside the power supply of most devices we use. Some will have external power supplies, and this fixes some of that. But anything that has a power supply inside the piece of equipment, transformer has some internal things going on where there are internal current paths. And these are tiny. We're not talking about the same current that's flowing through the transformer mainly, but there are some little stray currents that happen. And those are going to end up flowing into the case of the transformer, which is connected to the chassis, and thus they're going to connect to earth. Again, these aren't huge. None of these things are huge on their own, but we're adding little bits of current that are flowing through our earth wire when our earth wire was not supposed to have current flowing on it. So let's get back to thinking about what happens when current flows through a wire. So remember that wire is a resistor, capacitor, inductor, has all that stuff going on. But if we just think in simple terms of a resistor, what happens when a current flows through a resistor? It drops the voltage. But what does that mean for us? That means that the two ends of the wire are now at different voltages, right? If the wire is dropping voltage, then that means there's a voltage difference between one end of the wire and the other. So they are at different voltages now. So there's also the capacitance and the inductance. Those are going to change things. Those are going to add extra bits to this, but probably not significant. But still, there is some effect of that, and you can get wire that is better at this than others. And that's something we'll talk about later, but just as a starting point, those things are happening too. So we know that now we have two ends of the wire that are at different voltages. So if you connect earth at the outlet, and you have an earth wire going from there to your device, the voltage, if you measure voltage between earth at your outlet and earth at your device, there's going to be a voltage difference between those two. Now, if it's just a single piece of equipment connected, we don't really care about that. That's not going to be a big deal. And we are talking, maybe a volt at the most. It's not anything significant. You might see a couple volts in some situations, but not huge voltage. Certainly nothing that's going to endanger anyone. This is not a safety hazard, which is why it's all legal for all this to work this way. It's still a safety. It still works. You can still touch it. You won't get injured. No problems there as far as safety. Sort of another thing to consider is that means that if you had different outlets in the same building, there's an earth wire between them, so there can be differences, and there could be a difference between the earth connection at one outlet and at another outlet. In audio, we can think of that being, so you've got a live sound system with a front of house console, and you've got a power cord running from the stage to that front of house console, because that's an easy way to do it. That might be a couple hundred feet. It'd be a really long power cable. So there's a big voltage difference then, big as in a volt or two, between earth at the stage, where everything else is plugged in, your power amplifiers, speakers, musical instruments, and the console, earth out there. So let's sort of think about what that means for us. And we'll stay in that situation of we've got a console and a power amplifier feeding some speakers. So we've got this fancy console, need to connect it to power, right? So we got a power connection. So what do we now know about the chassis of that mixing console, assuming it's a metal chassis, and the earth connection at the outlet? So we know that there's current flowing through that. We talked about why there's current flowing through earth. That means that the voltage measured between the outlet earth and the console chassis earth, there's going to be a voltage difference there. Again, not a huge one, but there's going to be some amount of voltage difference there. And it's going to have a little bit of sine wave on it, a little bit of sort of random noise stuff that we're filtering out, maybe some RF, a radio station video sort of signal. So it's not anything we would want to listen to, right? It's all just noisy stuff. Got ahead of my slide a bit. Remember, we've got all those things that are causing this. We've got the induction from neutral. We've got the noise filtered from the earth, from earth to to earth from the AC inlet, right? That's all the other devices are causing distortion on the power. We have to filter that out. Transformer, other components are going to add some stuff. So all those things are causing current through our earth. That's causing that voltage difference. So we probably want a power amplifier too. Now maybe this is built in the speakers, maybe not. I put one on here that's not built in. Right, we're gonna have to plug that into power. Same as we do everything else. So the same thing's gonna happen So the same things are going to happen, right? We have to have that power connection. All those same currents, all those same things are going to cause current to flow through our earth wire. The amount of current flowing hot and neutral on this power amplifier compared to the console is probably going to be a lot more on the power amplifier. It's probably in a different location, so there's different noise getting on it, different filtering possibly happening. So again, there is noise, there's current flowing on the earth, but it's not the same current that's flowing on the earth from the mixing console. They're not going to be the same. Even if we had two of the exact same devices, there's going to be some differences in the amount of current that's flowing on earth and exactly what that current looks like. Again, the same things are causing it, but it might be slightly different. In fact, it will be slightly different. So now we've got our mixing console and we've got our power amplifier. And we know that both those chassis are going to have a voltage difference between them and the earth connection at the outlet. In sort of a simplest situation, we would have ground of our audio circuitry connected to earth as well. So let's say we've done that. So now we're going to need to connect to get audio from our console to our power amplifier. So we're going to use a balanced connection, which we'll be getting into more detail on later. So let's say we've used an XLR with a balanced connection. We've got our cold connection, our ground connection, and our hot connection. So we've connected those together now, as you'd expect to. And we've connected audio ground to the earth and chassis connection on both of those pieces of equipment. And that is the most common thing to do. We don't have to. There's some ability to change that, but that's what we're going to start off doing. So what's going to happen along that audio ground wire now? So we know that there's one voltage on the mixer ground, a different voltage on the power amplifier ground. So if they're at different voltages, then current is going to flow through them. So let's just take a single moment in time, because this is all AC, so current's going to be flowing back and forth. But at any single moment in time, we see current flowing from the mixing console through the audio ground to the power amplifier. But we know that current has to flow so it gets back to where it started. Otherwise, it can't happen. So it's going to flow from the mixing console through audio ground to the power amplifier, down through the earth wire to the outlet, back to the earth wire of the other outlet the mixing console is plugged into, and then back up into the console, making that circle or that loop along the ground wire. So we have current flowing in a loop through ground. That's a ground loop. You'll hear that mentioned, I would imagine you already have, but you'll hear that mentioned in audio a lot. It is a problem. It's something we need to fix. And how we fix that, we'll be talking about. One easy way to fix it, all we really need to do, right, is make it so that there's not a connection to this loop. So at any point we can disconnect this loop. A physically easy way to do that would be using one of those grounding adapters without using the screw to ground it properly on one of these two outlets. So let's say we want to go worst case and we do it at the power amplifier side. That means all that current and voltage in the power amplifier, which is most likely going to be much higher voltage than is at the console, is available to short to the chassis. And then the chassis is not connected to anything except the audio ground. So the ability for that audio ground wire to be a better path to earth than you is not as likely as it would be if we kept the earth connection. That earth connection is there for safety. We do not want to disconnect it. But if we did in this case, we would stop our ground loop from happening. We'll talk about why we don't want a ground loop and what problems it causes coming up. But this is the reason that it exists, and this is why it's called ground loop. Hope this helps. Let me know if you have any questions.